Thanks for coming out this first physical colloquy after the pandemic. And today we have a great pleasure to invite Professor Chang Tien-Hsien from the ASIAA quarter. And Professor Chang is an expert in bioscience, and there's a many detailed field. But let me just briefly introduce his education and some previous research experience. And Professor Chang got a PhD from the University of New York, Buffalo in 1986, and got a postdoc fellow at the Caltech from 87 to 91. And then later he became the assistant professor at the Ohio State from quite a long time. And later he returned to Taiwan in 2007 as a research fellow at the Genomics Research Center at the AS. And he got a numerous awards on different fields, including some of the best outstanding teachers from the Ohio State, and also other academic awards. And today he will be sharing about some of his own research and experience. I hope that will be helpful and interesting to all of you. And the talk might be slightly longer than an hour, but if you don't mind, I will encourage you to stay. And I leave the stage to Professor Chang.
Thank you. Thank you. First, I would like to say that this is a great surprise to me, myself, as a biology to speak in Institute of Astronomy. And you may wonder how this possibly could happen. It turns out that Ken and I were FB friends, Facebook friends. And I don't know him at all. This is the first time I ever saw Ken today. Okay, so one day Ken sent a friend invitation on the FB, and I said okay. So then we became friends, and later on he invited me to come over to give a talk. And so I said okay, what should I talk? Now, I am no astronomist. I'm really an idiot of astronomy. So what I'm not going to do is to teach you anything about astronomy. Neither will I teach you anything about biology, because I imagine you don't know very much about biology. So if I get into too much biology, you will get lost. So, but instead, what I want to do is to reflect on my career in terms of research. How do you do research? Now, I'm at the age of 65. I don't know whether you can see it from me, physically speaking. So I'm entitled to reflect my own career. And maybe I will provide a little bit wisdom to share with you, and then maybe you learn something useful. So you look at the title, like I say, doing good science in good taste. Now, as a scientist, we train to be very rigorous in every single word we put down on the paper. So every word counts. I'm not just saying that doing science. I say doing good science. And then in good taste. Many of you would not have thought about saying doing science has to be in good taste, but I will tell you why you have to cultivate a good taste in doing science. Now, then you find that the subtitle would be an often AI. That's not astronomy intelligence. That's not astronomy intelligence. The reason, there's a very interesting story. So I am, if you don't know, I am responsible for Academia Sinica's Research Integrity Office. I'm the director of the Academia Sinica Research Integrity Office for education and consultation. So once I was invited by the Minister of the Science and Technology, MOST, to talk about research integrity. Now, he said that, oh, we have so many talks about what scientists should not be doing this, should not be doing that. This is not right. This is ethically problematic. Why don't you talk about something positive? Something scientists should do, should instill themselves a sense of excellence. And I say, all right, I can try. So I come up with this particular title, right? So doing good science in good taste. And then often AI. The reason I put AI right there is because at the time our minister is the biggest promoter of artificial intelligence. Tien-Hsien, okay? So I want to make a joke of him. And I intentionally want to make a joke of him. So I was expecting he's going to introduce me as a speaker, but that day he didn't show up. But what I meant is abandoned intelligence, AI. The reason I say that is abandoned intelligence is that for youngsters sitting right here, even for junior PI, many of you will know that you have to do research, you do experiment, you do observation, you do quantitation, you do calculation, you do simulation, etc. And then you publish paper. And that's how you are major. But I don't know how many of you ever thought about, say, okay, have you ever thought about what is my real contribution? Getting more papers? Is that what we need in Taiwan? Now, as Ken said, that I worked many years in the United States. And later on in my last slide, I will tell you my trajectory, my own pedigree. Okay. So I learned from very young that when I do science, I have to do important science, not just science. So, but in Taiwan, this is an often abandoned intelligence. It is people, you are measured by the number of papers you publish. They quantify you by impact factor. And those are all very biased or not really good idea. Okay? In the United States, when I was up for tenure and promotion, PNT, I was reviewed by 12 external reviewers. They were asked to write letters about my research. There's not a single number there. It's narrative, 描述性, 叙述性, narrative way of assessment of my accomplishment. That's what we need. Okay, academic syndicate is beginning to make improvement on these things. That's good. Okay, so we emphasize in science doing good science. Now, if you can do good science and do large quantity of good science, that's terrific. But at least you have to build in your mind that doing science, you want to do good science. Okay, and then as I mentioned to you early on, I taught in United States at Ohio State for many years, and then I taught undergraduate, graduate level courses, and I kept talking the external educational things. So when I first returned to Taiwan, I immediately sensed that there's a problem of our education. I was away for a long time. In fact, prohibited to return to Taiwan because I was blacklisted, politically blacklisted. I really could not return to Taiwan for 13 years. That explains why I'm here, because I always want to come back, okay? Now, so teaching the Taiwanese student, I immediately found that there's a problem of our education. So then I tried to coach them to do well in graduate school and to be really learning something useful in graduate school. So I was invited by Taida, National Taiwan University. Subsequently, somehow people know about me. They invited me to give a number of series of talks And then let me show you the talk title. It was pretty funny. Those talk titles were not designed by me, by the way. It's designed by the by host. I teach people how to give seminar. Now, people in the audience, you should know that is a very important skill that you have to learn in graduate school. We teach graduate students how to give excellent talks in the United States. We emphasize that. But this is so weak in Taiwan. That is the first sense I got from Taiwan. So then they taught me to say how to write grant proposal. And then let me tell you, my first experience of reviewing Taiwanese PI's proposal was horrific. When I was at the Ohio State University, I was asked by the Taiwan's most to review a big project grant. They sent me a huge package, and then I opened up the grant, I read it, and then all of a sudden, within a few minutes, I said, oh my God, these are so bad. How could PI write such a grant so bad? In US, this grant the only place that deserved for this grant is to immediately put into the trash. Then I said, oh my God, this is how Taiwanese run their research? This is how Taiwanese write their grant proposal? And then after coming back to Taiwan, I reviewed some more grants, and I found it's the same. They stand zero chance to pass in US to get funded. So I try to teach them how to write grant proposal. And then I try to teach junior faculty how to run their lab, how to establish a very vigorous and hopefully successful research group based on my experience. And you can see that this is a talk was very welcome. I'm going to give talk at the Academic Seneca and NTU again. I talked to graduate students. I said, this is how you should do to become a successful graduate student. Because so many of our graduate students don't know why they are here. They came. They thought that was an extension of the undergraduate education. But Ken and everybody, PI in there, know that is not the case. So there's a big gap. So I explained that. Okay, and then some students want to go out for application, and I taught them how to apply for school in the US. It's for fun. And then I talk about many students are so pessimistic. When I first returned to Taiwan, they say, oh, if I go into study biology, 一日生科，终身科科。Okay, it's bad. Also, 一日天文，终身科科. I don't know. So, but I try to explain to them that their graduate school is the way that you train yourself to become an independent thinker, so that you can go to many different directions. There are hopes. So I talk about that, and I think I have the qualification to talk about these things, not only because I worked in the US for a long time, because I also humbly believe that I have done good science. Witnesses by this kind of paper I published. And I know you are astronomers, you don't know what are these journals, but at least you recognize Nature, right? So I published a number of Nature brain papers. Those are very hard, takes a long time to get through, okay, and very competitive. And then Ken was asking me, who was my best graduate student? Look no further. Ray Yuan Zhuang. This is my best graduate student. He spent only 3 years in my Ohio State lab and got a PhD, published a science paper, first author paper. So I believe I know how to guide graduate students. I believe I know how to do good science. Although I don't have a lot of papers, and in fact, I refuse to publish an incomplete paper. That's my philosophy. And I will explain why I came up with that kind of philosophy. But with that kind of explanation, that explains why I found that Taiwan's postgraduate education has a deep-seated problem. Deep-seated problem. Looks like you see here, but the problem is right here. It's so deep. And what are the graduate educational problem? Number one is that our graduates came to graduate school by default. Few thought about why they want to be here. Few thought about their own future aspirations. So it's by default. So they thought I was an undergraduate extension, okay? And so they behaved like an undergraduate. But we all know that that is not good enough. Actually, it's pretty bad to be that. And we want to train our graduates to become an independent thinker. But what I heard from my own experience in Taiwan is that the graduate students often answer PI's questions. So why did you do that? With the following manner. 学长告诉我的. My senior taught me how to do that. I said, what about your thought? And you think about it. So that is the problem. Second, they have very poor essential skill. They don't give a good talk. They cannot write. They cannot communicate well enough with other people, let alone outside people. I'm communicating to you as biology, to you as astronomers. I'm communicating across the discipline. So few have that ability. But as a scientist, you have the responsibility to communicate your work to other people. So these are also essential skills, but we train our graduate students so poorly. They don't have enough essential skill. So that is the major problem, one of them here. Then many students behave very unprofessionally. When I was a graduate student and postdoc, long time ago, you say, oh, I don't play games on my iPhone, for example. But now I'm seeing my postdoc was playing the games in the lab. Very unprofessional. They did not realize that they are already professional. You are no longer just an undergraduate student, so they are unprofessional. And so I thought, after coming back to Taiwan, I thought I should try to change these kind of problem. So I designed a course called Framing the Critical Concept in Modern Biology, a Historical Perspective. The reason I want to do that is that when you learn in your career, in your professional career, you want to learn from the very best. Okay? But without knowing who are the very best, you actually are in the dark. You are randomly learning something. Or some people who are not very good. You are not going to be very good at the very end. And also, our student has a problem that they don't have historical perspective. And you may argue with me, well, I'm a scientist, why should I know history? I say, history is very important. Science is about stepping on the giant's shoulder to move forward. So you have to know the history. So you know why your experiment, why your result, why your finding is important historically and where. Without a strong historical sense, you don't know what are you doing, why your stuff is important. Okay, so I try to build historical sense so that I use scientists from the history that have done fundamental contribution to biology. You don't have to know about them, but you can think about in astronomy. There are some scientists, they've done fundamentally really breakthrough, paradigm shifting work. These are great. We should learn from them. So what I do is I design a course that we talk about people, talk about scientists and their science. But first and foremost, talk about people. So we ask why they come up with this question. How did they design experiment? Or what was their thought process? what kind of problems they run into, how did they overcome the problem, how did they then make a major step forward. So my hope is that by learning through these scientists, students get a sense of what is the important science, what kind of important question they should be asking. So later on, this course continued to develop into become a course called to be a scientist. So perspective and essential skill. The essential skill is that I think it is very important to train graduate students to learn how to present, orally, writing, and communication and networking. These are essential skills in science. And I don't think you're going to argue with me, those are not essential skills. But we have to build in our curriculum to train graduate students to develop to be a full scientist, an independent thinker. So then this will follow the spirit of that to build in with a historical perspective. And then so what I want to achieve is the following. I consider good science. How do you become what my goal for this course is 5 goals. I want to put students in historical context. Students rarely thought about historical context. They thought about science as papers from today and 5 years ago. That's their scientific view. But you tell me, any great scientist can come from without historical perspective. You must have historical perspective. So that is a goal I want to build. And then I want them to learn that science often is built on serendipity. I don't know about astronomy, and I bet it's most likely the same, a serendipity. If you don't know about this English word, check it out. Serendipity is like an unexpected happy finding. Okay, and you find something that was totally, you want to go east, then you find west. And totally unexpected. But when you think about it, it becomes a major direction breakthrough. So many scientific findings are serendipities. But then you ask the question, so why didn't everyone become great scientists? You find all kinds of strange things in your experiments, right? Strange outlier here and there, and why do you become a great scientist? Because you don't have historical perspective, because your knowledge is narrow, because you are not creative to think about any potential problems. Okay? Serendipity, synchronicity, this is especially in your institute. I learned from Ken, people are collaborative, so a lot of science is synchronized by people from very different backgrounds. Early biological breakthrough was done by physicists, chemists, and biologists. So they have to realize that. They have to know the importance of interdisciplinary conversation with other scientists, and then creativity. And then a lot of people talk about creativity, thinking about painting, thinking about musician. But the best science are creative. I always say that a science that was so exciting, so well done, is beautiful. It's pretty. That was beautiful. If someone tells your science that was beautiful, you should feel about it. Because science is essentially to a hardcore, at the core, are artists. We're creative. Let our imagination run wild. But then to put into the scientific perspective, to build logical argument, to use data to support it. But if you don't have creativity, then you just keep doing the same thing over and over again, making tiny step forward and tiny step forward. By the time you retire, you might ask you, so what is your contribution? Describe to me in one sentence, and you struggle. You say, I have done this, I have 50 points, but none of the 50 points are important enough, right? So I want them to build that. And then I want them to learn to ask critical questions. In this universe, that is pretty appropriate to this institute universe, There are so many questions. I can pick 10 questions from this floor. But the question is that, are these 10 questions of equal importance? Should they deserve equal time to be investigated? The answer is no. But what are the questions you want to ask? What are the questions you want to address? What are the questions you're going to pick? You don't know. You've got to train yourself to do that. So you have to learn how to ask critical questions. And I argue you have to have a good taste. If you don't have a good taste, you don't know what are the important questions, critical questions. And I will explain what is good taste. Okay, because this will be coming as a very big surprise to you as a scientist, that scientists are talking about taste as if we are chef, cooking a spaghetti or something. But in fact, in a sense, we are chef. We're doing an experiment. We are mixing things together. We are imaginative too, right? So you have to develop good taste. And then lastly, in this course, to be a scientist, I wanted them to build transferable skill, giving talk. And when they get out of graduate school, they are very confident. They are capable of coming quite close to me as I'm performing right now. Okay? And with all kinds of skill built up, then they can become independent scientists. So then let's ask the following question. The title will be in Hanzi, 中文, but you will understand anyway. We ask the question, what is science? 科学是什么会? Okay, so you see this particular slide, completely dark. No, you have a very good observation because there are two eyes right here. So you speculate as a scientist or as anyone, there may be a cat there. But this is a room that was completely dark. In fact, cat's eyes are not going to be lightening up. This is just for the special effect, for your imagination. But I would argue the essence of science is to find a black cat in the dark room. So it is hard to find a black cat in the dark room, especially if the cat is not there. Right? Think about your own discipline. I bet you feel the same thing. Even in astronomy, my imagination is that sometimes you imagine there's something, but you actually have nowhere to get there in the dark. You're looking in the dark. Science is finding a black cat in the dark room. So sometimes the black cat was not there at all. That's the essence of science. That's not engineering. Engineering is very different. Engineering is based on a prototype. You want to improve the prototype. You have a goal, you get there. But science often does not have a very fixed goal. You want to uncover something, develop knowledge, new knowledge. Okay, so that's the essence of science. Okay, so scientific research is just like finding a dark cat, a black cat in the dark room, but you need tools to find it. You need tool. The tool is that you need a scientific skill and discipline to find it. And that is, you need some kind of light to find the black cat. So the way I look at science is that it's just like I opened up this door when this room was completely dark. And I heard there's a sound, and then that made me speculate that there may be a small animals right there. And then I just come in here, I don't have anything, I have only one this lamp, and then I shine on this corner, look at that corner, try to find the black cat. So in science, we never really look. That is very fitting in this department, this institute. You're not going to learn everything about the universe. You learn a little bit of window of the universe, and you try to generalize it. hoping that model is correct, that can be generated. So science essentially is about what? Let me summarize as the following. It's about unknowns. We don't know. We don't have the answer. I once had a graduate student back at Ohio State, and then she often does the experiment, the American girl, and then she does the experiment, and I would tell her, say, well, this is good, but you can go back to do better. And she come back, and then I can say, this is better, but you can do better. Finally, she was pretty straight to me. She said, Dr. Chang, why don't you give me a project that's know that we know the answer? I said, then that's not science. If I know the answer, why should I study? Science is fundamentally about unknowns. And then scientists are the group of people who have the curiosity and knowledge to study unknown. So if you decide to pursue science, if you lack up curiosity, you just don't have the curiosity, I advise you not to do science, because you're going to find it very painful, because you're going to live in unknown, okay, all the time. And then you have to develop the knowledge to pursue the unknown. And so you went out for exploration, 去远足，去探险. Science is about exploration. Explore the unknown. So you sweat it out. You went to the west, that didn't work, went to the east, etc. You have to really sweat it out to do that science. Then you come to unexpected result. So I thought it should be this, but it turned out to be that. And I have no idea why is that. You have no problem, just cannot explain. You struggle. That's part of science. You struggle. And so at the very end, you are forced to come up with some sort of hypothesis. Hypothesis, plural form. And then you say, okay, let me test this. Let me test that. I rule that one out. I rule this one out. This looks right. So that leads to new exploration. To continue. Science is about that. That's the nature of science. I assume astronomy is the same as biology in this spirit. And you guys all know about this guy, so I don't have to explain to him. He once said the following thing. If we knew what it was we were doing, you wouldn't be called research. Research is about exploration. Even Einstein does not know. He explored. Then he found some general rules. And in fact, if you look at the word research, that's very interesting in English. Research. You search and search and search. We scientists never arrive at the fine end point. We can call it the end. In science, there's no the end. There's unexplored territories, uncharted water for us to go on. Often you find something important that opens up a can of worms, many other questions that you have to ask. We're not going to figure out all the so-called truth. We are approaching the truth, but we never arrive at the so-called absolute truth. So it is hard to say we prove something. Proof is a word that was often used in mathematics, because within this system, it's absolutely proof. But in biology and in astronomy, I guess you cannot prove anything. We approach a model that is the best to explain all the data. All the data are consistent with the working model. We do that and keep improving, okay? So science research is often not students in coming to science, they would think, okay, if we started with A, then we would end up with B, okay? And the route would be very simple. We follow the protocol, we run this computer program, we do this and that, we do this statistic, and then you will go from A to B, and go in that. That's the imaginations from the young graduate student. This is this way. But experienced scientists know that that is far from the truth. What is the truth? Is that science is this. You explore, you run it around, you waste your time, and you got frustrated. You even get depressed. You want to give up. And at the very end, you think you're going to find B, but actually you find a bag of junks. Right? So in your experience, you must have found a lot of junks before. You got so excited, but then you end up with a junk. But occasionally, you explore, you're going from A, instead of going this, you try the other routes, ends up with diamond. Then that's important. That's an important discovery. But then the question then becomes, how do you know you find is this instead of that? So I often taught my graduate students say that the best scientists know their results are junks or diamond. Poor scientists thinking their result is diamond, but instead actually they are junks. Or thinking their results are junk and throw it away. Now, that happens in science a lot. Inexperienced graduate students sometimes throw away very important piece of data, observation. Why is that? Because they are not well trained. They are not being mentally and intellectually discipline to a point that they can differentiate the two. But to differentiate the two, that requires a lot of skill and perspective, intellectual and historical perspective. So we wish that we can try that. So that is involving good taste. Without good taste, you're not going to differentiate the two. Okay? So now let's talk about good taste. But research on what? Okay, so we often, the young students or junior PI often ask the question, so what kind of question we want to ask? What are the important questions? Research on what? So I would suggest the following. There are several kinds of research. And a typical kind is, I have been doing this ever since I was a graduate student, so I continue doing it. I continue to do what I have been doing. Okay, that's one reason. Okay. Second, personal interest. I developed a new interest in this. Instead of studying moon, maybe I want to study Mercury. Okay, good. That's another good reason that you want to develop scientific question. And sometimes it's trendy. Black hole is so trendy, so I want to jump into a black hole. That's okay. But then the question is that you have to ask yourself, what can you really contribute? After so many people have done it before, what are your unique angles? Okay. Also, you can in biology, you can stem cell, all kinds of things, very trendy, sexy topics that you can do. But what I would suggest, you should, as a researcher, identify the critical knowledge gaps. Gaps. As I have alluded to you earlier on, in science, there are always unexplored territories, unanswered questions, mysteries. Then some of them could be very important. So you should learn to identify critical knowledge gap. Now, all three words are important. It not only can be a gaps, or there are gaps all over the places, but you want to know where are the critical gaps. And I will come back to explain this a little bit more. So you hope that you make major contribution. It's not just a tiny little bit. I have been doing this every day. So for biologists, I work with, I work a liver cell. Tomorrow I work with a spleen cell. I use the same technology, get the same type of result. It's boring, okay? You want to make important impact, so no incremental impact. So what are the critical knowledge gaps? How do you identify them? The critical knowledge gap, first one, you need historical perspective. If a scientist without historical perspective, the scientist living is within 5 years of time, never learn how to address an important question. Okay, it probably can follow the trendy thing, but nothing more than that. Okay, then second, the critical knowledge gap often come from community consensus. So that's why I explain to youngsters like you, not people here, you have to talk to other scientists. You have to go to meeting, talk to people, then people would discuss, and then there are people talk about something unknown or potentially very important. You learn something. They are the knowledge gaps. And so when sometimes you think about, I come up with, this is an important question. My advice is that then run it through your friend, expert, and invite very harsh critiques. Because sometimes your imagination actually take you away. And you are kind of not really thinking it straight, okay? Now, in the past, as I'm gonna later on to show the picture, okay? All of you probably know about double-strand DNA, right? And the two people who discovered double-strand DNA is Watson and Crick. Now, Watson and Crick, a lot of things, when they uncover double-strand DNA structure, a lot of the time what they do is talk. They talk to each other. They talk to other scientists. And then maybe Watson will say, hey, this is a great idea. And then Ken will come along, well, that's bullshit. Okay? And then why that is bullshit? And Watson will say, well, right, okay. That's very important. Critiques from other people. And you have to think about whether that's technically doable. Identify a good knowledge, important knowledge gap is good, but sometimes that cannot be solved. The current technology just not possible. Either you have to create such a technology, or you have to come up with something different. You can dream, but you don't want to dream impossible dream. Okay, so that also have a certain level of realistic, and then hopefully your science will have a wow factor. So as my student often ask me, so what do you want to do? How can I get my paper to Nature? I say, you ask yourself, does your paper have a wow factor? When people see it, they say, wow. And if they don't, and then if you take 15 sentences to explain your finding, then forget it. Don't worry about it. Then you just waste your time. Okay? And I will elude on that a little bit later. So, this gentleman right here, whose name is George Whiteside, is a Harvard chemistry. George Whiteside used to be this is external academic reviewer, the chair, okay, in our institute, right? George Whiteside, and
he's a material scientist.
He is a chemist of all trades. He does a lot of things. He published more than 1,000 papers. More than 1,000 papers. He's the Wang Qihui's PhD advisor. So he was invited to be served on our external review panel to review the Genomics Research Center. And then this guy is tough. So when you run into him, then you're going to explain, you're going to do a presentation to him and then a whole bunch of external review panel. Then he asked the following question. And I found out it's very illuminating, very inspiring, very interesting. Tell me your story in 1 minute. I don't want to hear any more 1 minute. 1 minute. And if you continue 1 minute, he lost interest. He said, okay, go on, somebody else. Okay, so here I'm going to getting to the taste part. Okay, he asked the question, why bother? Why do you bother to do that? Why do you bother to ask that question? Explain to me. That's good. Okay. Then he said, who cares? Who cares? You have to explain to me why you want to do this research. You don't want to go to 捡到哪里就是菜. Okay, go to the market and pick up something. Okay, I just want to publish one paper. That's not good enough. And I think that's very illuminating for you to think about your own research. Okay. Now, when I teach the course of the toward a scientist, I use a textbook. I don't teach them really. I ask students to read it. You can download it from the internet. It's free because there's no copyright. Okay, this is called The Art of Scientific Investigation. When I first came across this particular book, I immediately have a question about the title of the book. The art. Art? Scientific investigation, I understand. But he said, the art. Art. But now seasoned scientists like the PI, several PI right here, you gradually have a taste that science is sort of an art. Scientific research is sort of an art. It was very nice. It was written by a Cambridge professor, okay, in 1953. Still very, very good book. I asked my students to read it, and then they would present to the class. Form teams, and they will present to the class. Okay. Now, in one particular chapter of this particular book, so this is my question. So, one particular chapter, he devoted to taste, scientific taste. So, for example, right here, taste, a sense of beauty or aesthetic sensibility, reliable or not. He doesn't know, reliable or not, depending on the individual. So good scientists develop good taste. And then it's much more reliable from their own past education, mentorship, or personal exploration, personal critical thinking. They develop a great taste. It's much more reliable. Some are not very reliable, but it's really a beauty of thing. Okay, now these scientists, these great scientists, such as Whiteside, they simply feel there's a particular lines of work of interest. Somehow there's a gut feeling. This is important. Okay, now and worth following, but perhaps without knowing why. That's the beauty of the scientific research. Sometimes you have a gut feeling. This is very important. You follow your gut feeling. And great scientists have great gut feeling. Poor scientists have lousy gut feeling. So he talked about these tastes, and he further said that the person who possesses the flair, means the ability to have taste, has the habit of using imagination to look far ahead. Scientists is not just doing the experiment, not only just about running computer programming. It's about imagination, about art. May be able to state explicitly the reason why or envisage any particular hypothesis. May not. Sometimes it's just gut feeling. They cannot know. But it's because their own training over the years. They develop a great taste. They know that this is an important question, worth pursuing, and then worth be persistent to solve the problem. And I would like to train our graduate students to be able to equip with that. And I would like to see our young PI to be able to push themselves to that level. And I think that's very important. Otherwise, Taiwan's scientific capability or level will be staying always one notch below some of the best places. We need people to be creative. We need people who have good taste to do science. And so let me share with you 4 personal stories about my own growth to develop taste. Okay, so these are biological stories, but I try not to get into my biology. But when I was a PhD student in the second year, so you can imagine how old I was at the time, 22, 24, 26 years old. I was 26 years old. And I read a paper talking about RNA. Now you all heard about RNA, right? Moderna is the messenger RNA vaccine. You at least heard about RNA. People in the field for a long, long time, in all the biologists, chemists, they all think enzyme, 酵素, okay? Enzyme can only be protein, 蛋白质. Enzyme is protein. That's conventional wisdom. But this paper I read, they say RNA can be an enzyme. It can catalyze itself to do its catalysis. So when I was a second year graduate student, I come across this paper. Now I want to emphasize I was a second year graduate student. So what are our second year graduate students here in Taiwan? What are they doing? I was a second year graduate student. I read across this paper and then I look at it. And I said, this is so unusual. This is unconventional. This is just incredible. If this guy is right, the biology is changed. It fundamentally changed the way how we look at the universe, look at the origin of life. It came into my mind about that, a second year graduate student. And I don't know why. I don't really know why. I just thought, and then I immediately come to the conclusion that if this guy is right, he's going to get a Nobel Prize. And yeah, he got a Nobel Prize. So that's my second year. Obviously, somehow along the way of my education in Taiwan, I was not conventional. And I told you that I was blacklisted by Kuomintang. I could not return to Taiwan. I was a little bit an outlier all the time. I never really want to follow the rule very closely. I think a little bit differently. Now, when I was doing my postdoc at Caltech, and so the field was reached at the stage that there was a hypothesis saying that there's certain enzymatic activity right there. There's an X factor, let's put it like that, in the field. But nobody knows how to do that. But I identify that is very important, that I chase against that. Nobody knows how to do that. I was going to a dark room to chase black cats. And I don't even know those black cats are there. Luckily, I was at Caltech because my advisor doesn't care about me. At Caltech, nobody cares about you. You are supposed to be very good to become into Caltech. So nobody is teaching you anything. You learn by yourself. And my advisor was very nice. You're going to see his picture later on, John Abelson. When you talk to him about your idea, and he will say, oh, that's great, no problem. Okay, and he walk away. And then when you have trouble, he will help. Let me tell you a real story. When I first struggled in his lab for the first 4 months, and because he's the U.S. National Academy of Science member, he was a big-time scientist. He was traveling all around the world, hardly ever was in the lab. We are on our own all the time. Occasionally, he come back to the lab and chat with you a little bit. And one day, he came back from a trip, and I was the only one in the lab at 8:30. So he came in and he said, hey, how are you? I said, hey, how's it going? What happened? And then I said, okay, well, John, I did this experiment. Well, as you suggested, it didn't work. And he said, oh, okay, well, let's try this. Have you done this? I said, yes, John, I have done it. B, I have done it. Thought it, done it. Didn't work. And how about C? Thought it, done it. Didn't work. D, thought it, done it. Didn't work. Then by that time, he looked at me, stared right in my eyes, and with a cup of coffee right there. And he looked at me and said, become very serious. He said, I'm sorry. I think you're stuck. And he picked up his cup and he walked away. That's my advisor. He thought about it. And when I come up with this project entirely on my own, you have to do everything on my own. He's not going to tell you what to do, okay? So that's Caltech, okay? Now, he said, great, no problem, good idea. Walk away, right? And when I struggle, I didn't get it to work. And he said, oh, okay. And when I really got it to work, he is a great scientist. He instantly knew about this is a huge breakthrough. And then later on, he gave talk on my finding. He said, this guy opened up a new window, allow us to get into a new field, open up a new field. So why did I know I have to chase that factor X? I have a gut feeling. I have the taste to know those are very important. So that's how I brought that to Ohio State University as an assistant professor, continued to study my finding independently. And so during that time, I accidentally, by serendipity, okay, happy finding at the very end, find a gene that everybody calls essential. That means that, okay, well, the lights are essential for this room to have a light. And then you turn it off, nothing happened. This room is dead, right? So I accidentally find that you can actually take out all the light, and then the room will still be lighted. And that was so unconventional, so unbelievable. And even I doubt what I found was correct. I have to ended up doing the experiment myself many times, over several months, and then keep ruling that one, this possibility, ruling that one up possibility. But I knew by that time, I have found something that is so important, so unconventional. I had the taste. So when I told my graduate student, Jeff, he's a Taiwanese guy too, he doesn't believe me. He doesn't believe me. He thought that Dr. Chang, you must have made a fucking mistake, right? Right? So that could not be possible. That could not be possible. So even by the time we nailed it down, and I was jumping around, and he didn't understand why that's important. I said, I told you, Jeff, this is gold mine. You dig it, you find gold. I told you, do you remember that several years ago? At the very end, he did not believe that I could get the paper published in the top journal, such as Science. He didn't understand why. But it was a science material. So what I'm telling you this story is just several personal stories. So how did I come to this appreciation? So my advice is that you have to gradually cultivate it. It's not going to happen overnight, but you have to keep thinking about it to get your taste better. Okay, so that when people hand you $1,000 bottle of wine, you know that's $1,000 bottle of wine, not a cheap wine. And then when people hand you a $10 of wine, you don't mistaken that is $1,000 of wine. In science, that's the same. You have to cultivate your taste. And then the last story is about when I was, again, a faculty member at Ohio State University. I told you early on I was teaching biology 113. I have 650 students, right? So I have 12 TAs, right? I told you that. So one of the TAs happened to work in next door to me, an Indian TA. Indian, Yes, I am an Indian. That kind of Indian guy. And he was a nice guy. We chat a lot. Sometimes we work late at night, and then so we chat a lot. And in my teaching, one thing I do is that in October, that was the time when Nobel Prize was announced. It's coming up, okay, soon, very soon. In September, late September, October, Nobel Prize will be announced. And when the Nobel Prize was announced, I typically, because I go into my office at 7:30, my teaching was happening at 8:30. So I open up my computer, read the New York Times, and then lo and behold, this new Nobel Prize an announcement. If I found that announcement is important, related to the teaching, I would put it immediately into the teaching that day. And then I would explain why that is important, why they deserve a Nobel Prizes. And then I told all the graduate students that you must remember because I'm going to test you in the exam. So you have no place to escape, right? And so that happened to that day. I was talking to this Indian student. I explained that, in the next few years, Nobel Prize is going to be awarded to ribosome. You don't have to know what is that. Structure, ribosome structure. And then I said, and it will be awarded to these guy. That was the night. Okay, I was having a chat with him, and he said, yeah. When the Indians say yeah, that means no. When they say yeah, they do this, right? So the next day, I opened up the computer, read the New York Times. Ribosome was awarded Nobel Prize. Exactly 4 people, those 4 scientists, be awarded for Nobel Prize. One of them is an Indian. I told him already. So by the end of my lecture, he came to me, Satya came to me and said, Dr. Chang, you must be cheating. How could you be so accurate? How do you can even know that ribosome is going to be awarded for Nobel Prize and 4 scientists, these 4 and one of my fellow citizens, Indian, will get a Nobel Prize? I said, this is my profession. I keep cultivating my acuity, sense of knowing where to go, what are the importance. And this is something you have to do. This is something we have to train our students to develop. Okay? So when we think about Nobel Prizes winning, it's very interesting to think about what kind of thing would be awarded for Nobel Prize. I don't know whether you thought about that, but I thought about often when I was young. Number one, I think is definitely fitting to your field. Paradigm shifting. Shift the paradigm. Black hole, whatever. That fundamentally alter the way you think about the world, the universe, the life. Okay? Or you have a high-tech breakthrough. Previously impossible experiment can be done. That allow you to reach a new territory that have not been explored before. That also deserves a Nobel Prize winning. And then another one is against all odds. That everybody say that's not possible. Then you make it to work. And then the example I cited there are biology example. So I don't have to go into that. But you can think about your own example in astronomy. All have a human health benefit or human benefits. I'm not saying only these 4 types of things deserve Nobel Prize. Sometimes it's a mixture of 2. And then there are other things as well. But it's useful to think about how people consider things in science that are so truly important. That you have to learn how to think about that all the time. So a couple of years ago, I invited a speaker from Columbia University. His name is Feinstein. Okay, I call it Feinstein. Okay, and then he has a TED Talk. You just type Feinstein TED Talk. Okay, watched by millions of people. He was a great speaker, and because I read his book and used in my course. So I invited him to Academia Sinica. It was a fun, fabulous success. Wow, so many people come around, they know about him, and he was a great speaker, and I ended up having a very long dinner with him, and then we almost got drunk, and we have a great time. One time he published a book. This is how I come to know about him. I read about a book review in Nature on his book called Ignorance, How It Drives Science. So what Feilstein was talking about is that ignorance is the driving force of science, because we are ignorant about so many things. We want to find out the answer in a good way. So when he was teaching in the medical school, so he taught to the medical students and then the graduate students about neurobiology, 神经生物学. And neurobiology, as he described, neurobiology had a textbook more than 1,000 pages long, and it was very heavy, like 6 brains heavy. And then after teaching neurobiology for several years, he found it was not very satisfactory. Students thought that if we learn all the facts, then we know about neurobiology. As a scientist, we know that's not true. That's not science. Those are facts. Those are Wikipedia. Those are Google facts, right? So he decided that he wanted to teach students to learn about science, scientific investigation. So he decided to open up a course called Ignorance in Columbia University. So he wanted to invite scientists from different disciplines, such as astronomy, physics, and let them talk about what is the important question that they don't know the answer, and they are very excited about and want to find out. So to help the student to cultivate a scientific sense, what is science? So then he didn't know whether the course will fly or not. And the first thing he has to do is to find people who want to join the discussion, right? So he probably will make a phone call to Ken and say, Professor Chen, I think you are very, very appropriate to teach this course because you are very ignorant, okay? So surprisingly, all the professors are so happy to join him, and he was becoming a very important course, and later on he wrote it up as a book. So, and then in my own life, I also benefit by being challenged by scientists. At the Ohio State University, I have this colleague whose name is Alan Lumbowitz. Now, people study in U.S., you know people who has the name with Witz, that who must be Jewish. Lumbowitz, okay? Lumbowitz is a big-time scientist at Ohio State. He is now U.S. National Academy of Science member. And so he recruited me to Ohio State, but he runs an empire. He has like 20 people in his lab, and he is a little bit arrogant, and he doesn't talk to people very often. And he's even shorter than me. So I learned quite a bit from him. He doesn't teach me, but he challenged me. Okay, so he's now at UT Austin. Okay, he's elected to U.S. National Academy in 2004. And he's working on these kind of very technical things that you don't have to know, okay, but doing very well. So he challenged me first when I was a junior faculty as an assistant professor, that I would call it a one-sentence elevator story. So let me play it out for you. One day I was waiting for elevator, and the elevator arrived, door opened, Lumbowitz was standing right there alone by himself. So I walk in there, standing by him. As usual, he's a pretty arrogant guy. He doesn't even look at me. Look at front. And then he would say, how are you doing? Doesn't even look at me. How are you doing? And now when I was standing right next to him, I said, good. I said, good. And he said, what do you mean by good? What do you mean by good? I said, Alan, we just have a paper accepted by science. That was the time he turned his eye on me. And then at that time, the elevator door is open. That was his floor. So he walked out the elevator. And I thought he was going to just walk away, right? So then all of a sudden he turned and then faced me. And then he pointed out to my face, said, tell me that story in one sentence. Telling me that story in one sentence. Jesus Christ, I used 5-6 years to work it out. You tell me to use one sentence. But I instantly cranked my mind and then boom, tell him one sentence. He said, good, keep doing that. And he walked away. He walked away. I went back to my office, sat down. I was angry. I thought I was humiliated. But then I thought it over and over again. I realized, yeah, Alan is right. Important science doesn't need a lot to be talked about. Often it's one sentence. And then the second lesson I learned from him is the following. You know, he published all in this Nature science paper every year. You think about it, every year, right? That was just amazing. How could he do that? So one time went to his office and said, Alan, come on. Can you teach me? What was your secret sauce to publish paper in this top journal all the time? And then his answer is, no, I'm not going to tell you. That's my secret. I said, come on, Alan. Did you recruit me to Ohio State? He said, yeah. Do you want me to be successful? Yeah. So educate me. Educate me. What is your secret? Now, he told me one word. He said, oh, well, okay. He just used one single word. I don't know that is appropriate to astronomy, but that's very appropriate to biologists. He said, evolution. That is probably important for astronomy. Evolution. He said, you have to put your research in the light of evolution so that can be a general, have a perspective. So when you write paper, when you do discover, you have to think about these things. Don't just think about as a phenomena. You think about as a long-term, big picture and know how to express that. I went back to my office and thought, oh, that was great education. And in fact, when I was young, I came across this scientist whose name is Dobzhansky. He was a very famous biologist. Okay, that he once said that nothing in biology makes sense except in the light of evolution. That was exactly right. I learned from great people to learn to craft my scientific art, to do good work. Okay, and so at the very end, when you discover something, it's all about telling a good scientific story. And then many students will look at this word story. But remember, you have to communicate your science to people. You have to tell a good story. The first time when I was a graduate student, I gave a talk. And then I run into some professor, and then they said to me, oh, that was a very good, nice story. I was not happy. I said, you should have told me that was a very good talk or very good seminar. What does it mean by story? I think it's cultural difference. In Taiwan, we think story is kind of not very important. Why don't you tell a story to the little kids so that they can go to sleep, for example? But storytelling in the Western culture, and as of now in Taiwan, we all know that it's very important. Students need to develop storytelling ability to know how to tell a good scientific story. And our concept has gradually been changed into the West concept. They learn how to do story. So Let me close my talk by saying that if you want to do a good science with good taste, we scientists love to talk about pathway, like to draw a circle, or cell is a circle, this, etc. Okay, let me say that, okay, it is you. As a scientist, you have to learn to ask good questions first, okay? Second, you need to develop good perspective. This question related to history, related to the wider view of things. You have to keep doing that, learning how to do that. And then you have to learn how to do good design, good practice, do good experiment, do the right thing, and you have to make good decision. Now this is important. Now many times in our research career, you would pursue a goal and then run into the wall and get it nowhere. And that is where decision need to be made. Should you or not continue to pursue? If you want to pursue, then you have to think about why it didn't work. Is there a limitation? And if maybe this is a dead end, maybe you should drop, maybe you should move on. So this kind of ability to make decisions come from years of training, years of safe training, to make the right decision. When I was with my postdoc mentor, John Abelson, I told you that he never cared about me, right? No, he cares about me, but he just never taught me anything. And I have one question always about why John is so good, why John deserves a U.S. National Academy of Science membership. So among our postdocs, we even ask the question, say, why John is good. He looks like a janitor. He have a beard. Later on, you're going to see his picture. Here's a beard. He wears short. He wears sandal. He doesn't look smart. When he talks, he sometimes stutter. Then nobody can figure. One time his wife came around, Linda, and then one of our postdocs asked him the question, say, Linda, why John is so good? And his wife said, I don't know. I don't know. So we were at a loss of why he was good. So as a postdoc, what I did is I observed him to make decisions. Often in our scientific career, we run our experiment, run our research tool over here. Then it opens up several different avenues. Everyone is potentially pursuable. But how do you make decisions? John never taught me, but I kept observing him, how he makes the decision. Then I get a conclusion. He always pursued the most important question. He never tried to pursue the easiest question. I really look like he's on drug or something, right? These two are his postdoctoral mentors. Two legendary biologists were John Abelson's mentor. So I thought about it and I said, John must have learned from them. And then if you ask me how did I become me today, it was because of John. And it was because of Crick and Brenner. There's a pedigree of coming down. Good scientists beget good scientists. And that is not because just genetics, it's because the conceptual learning, conceptual indoctrination deep in the heart of belief. So that allows us to do good science. With that, I would wish you have all the success in your exploration and great success in the future. Thank you very much. And I'm very happy to entertain any questions.
Yeah, thank you very much.